Hey everyone, welcome to Chapter 5. And the goal for Chapter 5 is to sort of extend all of our work from Chapter 4 and previous chapters to answer really one main question. How do we control our mechanisms precisely? So one thing that you'll notice in terms of structure and organization for Chapter 5 and Chapter 6 is that we're sort of going to alternate between concept and implementation. So something to keep in mind is that this chapter, or this section in particular, will focus on the concepts behind PID, which we'll talk about what that is and what that means. And then the next video will focus on implementation. And then the video after that, we'll talk more about concepts. And then the video after that, we'll focus on implementation. So keep that structure in mind as you sort of plan out how you're going to want to work through these next two chapters. But with that being said, let's get started. So the first thing that I want to talk about is just a recap on what we did in Chapter 4, right? So in Chapter 4, the main way that we coded our mechanisms is this idea of percent output, right? And the whole idea behind percent output was that you would pass in this parameter between -1 and 1 within your code, and that would correspond to some percentage of voltage that the motor would output at, right? So that's exactly what we did to make our motor spin. But the real question is, how repeatable is that spinning motion, right? The main question that we really want to tackle is, can we easily set the speed of that motor in easy to use units? You know, if you've taken physics before, if you have some exposure to angular rotation concepts, you'll know that revolutions per minute, or RPM, is a really big universal unit in terms of measuring the rotations of a motor. So can we easily set the speed of a motor in terms of its RPM? And well, what happens if your mechanisms are different, right? You could have a whole bunch of things attached to your motor, like an arm or, different flywheels for a shooter, which we'll talk about in the future. Like, how do we control the variability aspect of the mechanisms that are on our robot? And then finally, how do we go from something like motor output to an elevator position, right? Like, think about something that linearly moves instead of something that's just angular in terms of the motor shaft, right? How do we even know when we would stop moving, right? So one of the naive approaches that you might think in terms of like solving this problem is, well, hey, why don't I just set the motor to however fast I want it to move and then measure the amount of time it takes to go from, let's say, one position to another position if we're dealing with like something that slides forward and backward, right? Try to get that visual in your head, Let's say I want to move something from its starting position to its ending position. I could just measure the amount of time that it takes to go from start to end, and then I could just set a timer in code to actually move it from that start to the end position. The problem is that's not quite good enough, especially when you're dealing with mechanisms that need precise control. A good example of that is an arm. So we need to somehow be more precise with our ability to command things like a specific velocity for a motor and a specific position for a motor. So that's where we get into the concept of PID. So in order to introduce PID, what I like to do is talk about the end goal first, like what we actually really want to do, and then sort of work backwards from there. So ideally, right, in terms of making things super easy in terms of code and implementation, we want to give a mechanism, whether that be a shooter or an elevator, whatever it may be, some kind of a target or a set point. This could be 1000 RPM, it could be 3 inches forward, 2 meters backward, whatever it might be, right? We want to give it some kind of a target to reach, and then we want to make our motors move that mechanism to the target as quickly and as accurately as possible. So in order to do that, we can use something called a PID feedback controller. So here's the main idea behind that, right? And one thing I'd like to preface before we continue is that PID itself is a very complex topic. It's typically taught in very strong detail in college level robotics courses. So something that you want to know is that our goal isn't to get into like the nitty-gritty math behind PID. Our goal is to give you an intuition on what PID is, how it works, and how you can take advantage of it for your own mechanisms. So if you're more interested in like the nitty-gritty details of PID, exactly how it works, the WPI library documentation on that is perfect. That's exactly where you should go. It outlines the math perfectly on how everything works. So feel free to head over there. There's also tons of YouTube videos online that can explain the math behind PID. Our goal isn't to explain the math, it's to explain the intuition so that you can get to implementation as quickly as possible. So here's the main idea that we're trying to cover. So we want to be able to sort of understand where we are right now, where the mechanism is right now, and how we can adjust our mechanism's motion to get where we want to be, right? And it's effectively just a mathematical way to minimize the amount of error, and by error I mean that gap between where your mechanism currently is and what your desired set point is. So for example, if you have a shooter flywheel, which is the example that we're going to be working with throughout this chapter, if you have a shooter flywheel that's spinning at like 50 RPM initially, and you want to get it to 1,000 RPM, PID is that mathematical way to, as quickly as possible, minimize that error, right? And there are three main parameters that are involved in sort of the equation for PID. It's P, I, and D, which stands for proportional, integral, and derivative. And setting these values is what enables you to get to your target as quickly as possible. So in order to better understand this, I like to use this analogy quite often. So imagine the following scenario, right? You are driving a car and you want to you're driving a car and you want to move at 100 miles per hour, right? And you're starting stationary, right? So you can kind of imagine like, you're in one of those like Fast and Furious movies and, you're trying to like beat your opponent in a drag race, right? So you want to get your car moving as quickly as possible. Full disclosure, I haven't watched any like Fast and Furious movies. I don't even know if that's accurate. But anyway, you start with sort of what we could think about doing in terms of PID, right? So let's continue with the analogy. So let's talk about what P would represent in this context, right? So in this case, let's say you hit the gas and the car is moving. Once you hit 100 miles per hour, you start to take your foot off the gas, but kind of think about what would happen if you're in like a normal gas car, right? The car isn't going to stop immediately. It might start slowing down a little bit, and once you're under 100 miles per hour, you're going to hit the gas again. So you could think of P as if having a car that only has a gas pedal, and pressing down the gas pedal is what represents like that P value, all right? I is kind of like cruise control. So mathematically speaking, and if like the technical details, I like to include this because if you've taken calculus, you might know what an integral is, but essentially what's happening is it sums up all of the errors that your mechanism has previously experienced. So effectively what's happening is the I term will drag something towards your intended value. So it's going to try to pull you towards that intended value. So with cruise control, right, you kind of force your car to maintain a particular speed, and that's sort of the same idea here. And then with the D term, try to think about what happened if you wanted to stop in this situation, right? P and I are mainly used to get towards a target, but what about sort of dampening that kind of motion, right? You can kind of think like D as if you have brakes on your car. Now, as you build, it basically builds up as you get closer to your stopping point. So this is going to change the rate of your mechanism motion based on how much closer you are to your target. So if you kind of like a good way to think about this, right, is if you're going from 0 to 100, right, obviously you're not going to be hitting the brakes when you go from like 0 to 60, right? You're going to keep accelerating, right? But as you get closer and closer to 100, you might slowly start hitting the brakes so that you don't accidentally overshoot once you reach that 100 miles per hour point, right? So that's sort of the general idea here. Now, this is what a PID graph looks like when we're dealing with a motor's position in terms of radians. So one thing that you'll notice is, so first of all, right, let's just hyper-focus on this orange curve here, right? So the first thing you're going to want to notice is that we start from a position of 0 radians, and our goal is to make our mechanism stop at 1 radian of rotation, right? So one thing I want you all to observe is, let's start with this orange curve here, right? We have a Kp value equal to 21. So this is kind of like our gas car situation, right? If we have a super high Kp value, right, that means we're constantly flooring, so immediately we're going to overshoot, right? And then we're going to undershoot, right? But the moment we undershoot, we immediately go back up, but this time we don't go back up as much, right? Because now we're starting at a value that's closer to our target, right? So we don't need to actually overshoot we don't need to actually apply the gas as much, right? Kind of think about like if you're going 100 miles per hour and then your car coasts and now it's at like 98 miles per hour, you don't need to floor it to get to 100 miles per hour, right? You just need to like ease on the gas a little bit, right? That's sort of what's happening here, right? And you can see that process repeat, right? But because, of course, this is a mathematical scenario, you're not smart enough to understand that you need to actually hit the gas lightly. So mathematically speaking, the magnitude of your error does decrease, but it's still too high. So eventually you let go of the gas, right? And eventually you are closer, and you keep getting closer and closer and closer until finally you end up at the steady state you end up in the steady state where you're in this position of 1 radian. Now we can look at the Kp value of 11, right? And we kind of had the same effect here, but notice that the amount of time that it takes to overshoot, right, is a little bit longer, but also the magnitude of the overshoot has decreased, right? And you'll notice that it takes a little bit less time to end up in this sort of steady state position. There's also less oscillation, which in general is good for mechanisms. And then finally, if you notice a Kp value of 1, we do have a very small amount of overshooting, but eventually, we decrease our overshoot and we're in the steady state of 1 radian. So one thing to note is that obviously this is not a perfect sort of PID tuned mechanism, right? You'll notice that we're still overshooting every time, and it also does take like a decent amount of time with this gap over here. Let me see if I can get my laser pointer to make this easier. There's like a decent amount of gap from here to here before you actually reach your desired position of 1 radian. So if you want, I'd highly recommend to stare at this graph and try to relate this back to the analogy on the previous slide, and I think it'd be very useful. Now you could imagine, right, if we had this sort of blue graph with a PID value of 1, right, a Kp value of 1. Now, one thing to note that I should have mentioned earlier is that we tend to abbreviate the PID constants with a K, so Kp, Ki, Kd. That's just a convention that we use for code, but you can sort of ignore the K in your head and just think P. So one thing to note is that if we have this P value of 1, right, if we added a D term, then the magnitude of our overshoot would actually decrease. So this curve might end up looking something a little bit like this. Let's see if I can do this. So see how instead of wasting time in our overshoot, we end up directly going to our position. So that's really the power of the D term there. Now, another thing that, another situation where the I term would be useful is, let's say you have a mechanism that's sort of constantly hovering around like this position here. It's not really getting to its desired goal. If you add an I term, it'll sum up the errors that are occurring at each of these points in time, and it'll try to drive down your errors. So you end up getting something that looks like this. So of course these are just arbitrary visuals, but let's kind of talk about now what to expect when you're actually PID tuning your own mechanism. So the first thing that you're going to want to do is get a printout of your mechanism's position and velocity. And in Smart Dashboard, you can read this and even make it a graph, just like the one that we looked at previously. Like you can get a graph of your mechanism, of your mechanism's position in Smart Dashboard, which you will see how to do in the next video. Now, the first step that we recommend that we've seen before is set P equal to 1, set I equal to 0, and set D equal to 0. And we find that this is a really good starting point, especially for simpler mechanisms. So in this case, try to only modify P. So if you're overshooting, lower your P value, and if you're undershooting, increase your P value. The next thing you're going to want to do is set a D term. Now, if you're overshooting and lowering the P isn't giving you accurate enough results, and also if it's not giving you a result as quickly as you would like, so kind of like the situation where we had here, right, where we had this like period of overshoot that we kind of want to get rid of, that's when you would add a D term. And we recommend starting with a really small D term, like 0.01, but that of course depends on the scale of what your P term is, because depending on how your mechanism's units are, this P value of 1 might not actually do anything. You might just have like a P value of 10. Right? So it just depends on the magnitude of what your P value is, and scale these values accordingly. All right, and the next and final term we recommend is setting an I term. Now, in this case, we recommend that you set a very, very tiny I term, like 0.0001, and then go up from there if you absolutely need it. Now, from what we've observed, you will almost never need to set an I term, and for most mechanisms where you can have a decent margin of error, having a P term and a D term is more than enough. All right. So that is all that we have for a sort of quick crash course on the concepts behind PID. So in the next video, you'll hear from Griffin, where he's going to talk a lot more about the code side of things and how you can sort of work with the code implementation and also get some feedback and how to actually iterate through all of your code and tune your mechanisms properly. All right, so thanks so much for watching this video. I look forward to seeing you in the next one.